So, streamline flow. Streamline flow is properly defined as follows. We have already seen what it means the last time. If you remember, I told you that at every point the velocity is fixed, right? Okay, that is at every point velocity is constant, not uniform. May be uniform, may not be uniform. That's a different thing, but it should be constant, right? So let's write it properly. That if the velocity of fluid, not speed, remember velocity, at each point remains constant, that is, does not change with time. Okay, so at a particular point the velocity of the fluid remains constant. At that point it will have that velocity, it will never change. Then the flow is called streamline flow, or streamline flow. Another word for the same thing is steady flow, right? It's called steady flow. The two names were the same thing: streamline flow, steady flow. Okay. So whenever we are talking about a streamline flow, we can actually mark out the velocities at different points. Let's say that there is some tube like this, for example. Okay, this is the shape of a tube in which fluid is moving. So suppose at this point the velocity is in this direction. Okay. Then at this point, let's say the velocity is in this direction. Then at this point, let's say it's in this direction. Then let's say it's here. It's here, 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 and so on and so forth. So when we make all these different velocity vectors and join them, okay, when we join them, what we get is called a streamline. This curve, you see a curve? That curve is called streamline, right? Similarly, this is one streamline. Okay, let's say this streamline starts at point A, right? Then there might be another streamline. Let's say starting from another point B. Then it could be in a different way, maybe here and then here, like that. So what these diagrams show is that if a water particle or if a fluid particle starts at this point, then it will follow this path. Similarly, instead of starting here, if it starts here, then it will follow this path. Understood? Yes or no? Right? In fact, at any point, suppose you want to know the direction of velocity. Let's say I want to find the direction of velocity at this point. That is when this particle will come here. In which direction will be the velocity? Then the way to do it is draw a tangent. You understand how to draw a tangent? That indicates the direction of velocity at that point. Clear? That indicates the direction of velocity at that point. Alright? Okay. There are a few more things to understand about streamline. Okay, some important points about streamline. Again, this curve that we are drawing is called streamline. Right? So number one, two streamlines never cross each other, or even intersect. Forget about crossing; they don't even intersect each other. What is that? See, if you imagine that one streamline goes like this, the other one, let's say, like this, so they will cross. In such a case, there will be something strange happening at this point. Like I said, streamline indicates path. That is, if a particle starts at A, it will go like this, like that. Or if it starts at B, it will go like this and this. Okay. But now if two paths cross, so particle from here should go on this path. Particle from here should go on this path. Then there's a problem. The problem is when the particle reaches here, which path should it go on? Right? Another way to understand the problem is using more mathematics. Tangent. You understand what's a tangent? Suppose I want to draw a tangent at this point. It's impossible. I hope you realize it is impossible to draw a tangent at this point. Right? Or even if you do, you will have two tangents, one like this, one like this. But like I said, particle can only move in one direction. Its velocity can only be in one direction. I hope you realize that ultimately for every object, at some point of time, the velocity can only be unique. Right? एक साथ आम में बे velocity no. Then there is result. You understand what I am saying? There is only one velocity. So this is nonsense. Right? That's the reason why they cannot cross. Okay, two field lines. Two streamlines cannot cross each other. Right? Or even intersect. Intersect I say no problem. Number 2. The closeness. You understand that term? Closeness. That is how close the streamlines are to each other. Indicates speed. The closeness indicates speed of flow. Okay. Right? Closeness indicates speed of. What do I mean by that? Is that when the when the streamlines are far from each other, at that place the flow will be slow. The speed of flow will be less. Understood? If the streamline, excuse me, I am saying field line again and again because there is a similar topic in 12th standard. Okay. So, and these properties are exactly the same. Right? There is no difference between them. Nevertheless, so streamlines, when they come close to each other, that would mean the speed is more. You understood what I said? The closeness indicates speed of flow. Right? So wherever the flow becomes slow, the streamlines will spread out. Wherever the flow becomes fast, it would narrow down. Right? Things would get close to each other. Right? So that is what is indicated by close. Now, why does this happen? I will definitely explain the reason, but you'll have to wait for it. Okay. Right? When we derive some next property, next characteristic of flow, we will understand why this happens. Okay. So again, these are two things that you should remember. That they don't cross and closeness indicates speed of the flow of fluid. Right? Okay. This is only one type of. If you remember yesterday I gave you an example, an analogy with traffic. Vehicles go on particular path with some fixed speeds. Do you remember that? That whenever the vehicle comes at this particular point it should have 20 km per hour, when it comes there 30 km per hour and so on. Still remember that, everyone? That would be very nice, right? Everything would be in order, right? Steady. Compare that with another case where people are driving in random directions and with random speed. What's going to happen over there? Take vehicle, you understand that? Then it's not necessary that any vehicle that comes here should go in this direction only. Do you agree? It will go there also. Got it? Such a flow. In fluid also we have something like that. Such a flow where things change. Such a flow where things keep changing or things can change, that is called unsteady. This is steady. Understood? Such a flow where things keep changing, that's called unsteady. Right? Do we have to study about unsteady flow? No. Because like I mentioned, in unsteady flow, you cannot be sure what will happen. It's like one vehicle when it passes this point has speed 30 km per hour. But the next vehicle when it will pass this point might have speed 100 km per hour. And it might go in some other direction. Just like that. What happens to fluid is very predictable. You understand what I am saying? What happens to fluid is very predictable. In which flow? Steady flow. Fine. Same is true with traffic, isn't it? બધા આમ બરાબર વ્યવસ્થિત જતા તો એક્સિડન્ટ ન થાય, predictable. બધા આડે ગમે તે જતા તો throw a cow into the mix and it's such a chaotic thing, isn't it? Right? Okay, so that's where you have chaos, and in chaos things are very tough to predict. તમને એમ થાય કે આ ગાય અહીં ઊભી છે, હું અહીંથી આમ નીકળી જાઉં ત્યારે જ સાઈડમાંથી કોકા. Yes or no? Right? That is unlikely to happen on a long straight highway where people are moving with some constant speed. Correct or not? Okay. So that is the difference between a steady flow and unsteady. We are going to study more or almost exclusively about steady flow. We'll hardly study anything about unsteady. Okay? Because it is very tough to analyze and predict what will happen. Right? If you want to study about unsteady flows, you'll have to probably take up mechanical engineering later on, because those are the guys who study fluid the most. Right? Okay. So these are the things. Now, let's go on to the next thing that will also explain the reason of the sentence, and that next thing is equation of continuity. In my opinion, this equation is common sense. Right? You tell me whether you found it common sense like or not at the end of this talk. Okay, I'll ask you. Right? Let's see. Frankly, I think this is common sense. How samjhano hoy ne એવું મને લાગે. Okay? Let's start. Suppose that here is a cylinder, starting with the easiest case in the world. Let's say there is a cylinder, long cylinder. Okay, let's say there is a long cylinder, and there is incompressible fluid. What is meaning of incompressible fluid? What is meaning of incompressible fluid? It cannot be compressed. So what cannot be changed? Volume cannot be changed. Volume cannot be changed. Density cannot be changed. Clear? Ideal. Are fluids incompressible? Yes. Liquids are nearly incompressible. Gases are not incompressible. Let's go gases compressibility. Is it? Okay. So here. So let's say there is an incompressible fluid. Why are we taking that assumption? So that maths lets you study physics. Otherwise, the math itself will be so challenging that we'll have to forget all that. Right? So, consider that there is some fluid. Right? Okay? Now, do you agree that this is some part of fluid? If it is incompressible, that is, volume will not change. If this moves 1 centimeter, this end, let's say this part is where the fluid is. In an empty tube, if you try to make water flow, you'll see a little bit of water go down like this. Have you noticed that? Have you seen such a thing ever? So let's say this is a cylinder and this fluid is moving in it. 1 centimeter. If this side moves 1 centimeter, how much will this side? 1 centimeter. That is because it is incompressible. Volume should remain same. Make sense? Let's twist this. Let's change. Let's say this area here is, for example, 2 centimeters. And this is a narrow part, okay, whose area is 1 centimeter. Right? Actually, I don't even want to make it curved. Let's make it like this, so that maths remains extremely simple. Okay? I'm so sorry if you had to correct it. Let's say like this. Understood what I have drawn? Pitchkari powder. In a syringe also you have the same thing. Yes or no? There is a broader part and then there is the nozzle which is very narrow. Agreed? Okay, so let's say it's like now if there is fluid everywhere, let's say this is all completely filled with fluid, and here also there are two pistons. You remember pistons? Piston is an area over here, right, which is going to compress it or which is going to apply force on it. So now let's say that these are two pistons. Pistons can move, remember, up, they can go in, out, wherever you want. So let's say that this piston moves inwards by 1 centimeter and there is fluid everywhere. Do you realize that this piston in that case would not move 1 centimeter, it will move 2 centimeters? Yes? No? Who understood this already? Anyone? Okay. Immediately clearly in our mind it will take some time. Maybe I should go into a deeper explanation. This is how it works. Incompressible fluid means volume is constant. Yeah. So now if this goes inwards by 1 centimeter, the atlamadi fluid nikli jayega. Agree? If the piston goes forward by 1 centimeter, what is the piston? It's generally made up of metal. The fluid has to move. Do you agree? The fluid has to move. Now if the fluid will move, do you realize that the fluid will lose this much volume? Yes or no? How much is that volume? This area is 2 centimeters square. This distance is 1 centimeter. How much is that volume? 2 centimeter cube. Clear or not clear? Sure. So here it will lose or it will move a volume 2 centimeter cube. Clear? But because it is incompressible, volume should remain. So it should increase here. Do you agree? This should definitely move. Now think about it. How much should this move so that it gets that extra volume? If it moves only 1 centimeter, then it will get only 1 centimeter cube extra volume. Yes or no? So it should move how much? 2 centimeters. Agreed? So now how many of you have understood that if this is the case, if this moves 1 centimeter, this will move 2 centimeters? I hope it really is. And I hope you are not obliging. Fine? Clear? But the equation of confidence. In my opinion, this is definitely common sense. I think many of you agree now. Well, how do we write it properly then? How do we derive it? Okay, in the derivation we talk about the derivative. Instead of numbers, I'm going to give the symbol. Let's say that at one place the area cross-section area is A1, at some other place the cross-section area is A2. Does it matter if this shape is like this? No. Shape could be like this also. What only matters is the area. Shape doesn't matter, right? Area A1, area A2. That's all that matters. Now let's say that when you move the fluid, okay, let's say this fluid moves some distance x1. Let's say this fluid moves some distance x1. And over here this one should move some distance x2. We already got a relation between them. Now we khali symbol. So then do you agree that A1 x1 should be equal to A2 x2? Why is it so? Because volume should be 1. Sure? So an equation of continuity. Right? This is called equation of continuity. There is one more way to write it, and that is to do differentiation. We will do differentiation on both sides. d by dt A1 x1. dt, that is time. Okay, is equal to d by dt A2 x2. I think I did mention earlier that just like if someone tells you that x equal to y, then you can square both sides and write x square equal to y square. Similarly, if x is equal to y, you can always write dx by dt is equal to dy by dt. Differentiation is like an operation. If you do it on left side, you do it on right side. Got it? Just like squaring. Okay. So we need differentiation on both sides. Huh? This area of the tube in which liquid is flowing or fluid is flowing, tube no area doesn't change. If you make water flow in a pipe, pipe's area will change. Generally not, right? Because we don't make water flow at such high pressure. Okay, pipe fully. I hope you understand what I'm saying. If it is at very high pressure, then the pipe will expand. But we are not talking about those strange cases. So, A1 is a constant outside. What remains inside? I hope you all remember rules of differentiation. તમે યાદ નહીં રાખો તો કોણ યાદ રાખશે મેથ્સ વાળા બરાબર ને A1 outside dx1 by dt, what do you think we should call it? Distance moved, that is x1. So dx1 by dt should be velocity. A1 v1. I hope that's clear. Sure? Is equal to on the right side. Similarly, A2 v2. Got it? Again, this is only happening because of this. Right? The moment you ignore that assumption, I hope you realize how we got 2, 1 and 1, 2. You know Theorem, right? So that is equation of continuity. This one or this one, whichever you like. Generally, we use this. Okay, we use this more often, right? But let me tell you, both are the same. They mean the same thing. So this is something very important that you should definitely remember. Now, how does this equation explain that sentence? Right? Let's answer that and then we'll solve it. So, I want you to understand that first of all, this is only valid for streamline flow. Why we should use it only for streamline flow? Let me tell you. Because in streamline flow, the speed at this particular point v1 and speed at this particular point v2, these two will not change with time. Neither can one predictable side. અહીંયા કઈ speed હશે ત્યારે અહીંયા કઈ બીજી speed. So then you will not be able to get a relation. You understand what I'm saying? Right? Okay? કોઈ એમ કહે કે બે સ્ટુડન્ટના માર્ક્સ આવે એ બેને કનેક્ટ કરતી ફોર્મ્યુલા બનાવો. Impossible, because one person might get different mark, the other one different. Totally random. Yeah. If you can actually make a formula, then I can guarantee that those two copy from it. This is what है ना? You know, in the language of mathematics, this is called correlation. Correlation is બે વચ્ચે કઈક link નીકળે. You understand that? And links cannot be there due to coincidences. એવું બહુ rarely થાય that there is coincidence when everything is fitting each other perfectly, right? Okay, so like I said, we can use this only for which kind of flow? Streamline flow and incompressible fluid. Two conditions: streamline flow, steady flow, yeah, or and incompressible fluid. Yeah, there is an end to it. Everyone, this is equation of continuity. Sure. Okay, all the same. Am I erasing everything on the board? Is that okay? Yes. So that sentence, the sentence was closeness indicates speed. Let's see how. Suppose this is streamline flow, steady flow in this tube. So do you agree that particles over here should be flowing somewhere like this, particle over here somewhere like this, and particle over here somewhere like this? Agreed? Okay. At which place, where the area is more or where the area is less, are the streamlines close to each other? Where area is less. Look at that equation. V2 upon V1 is equal to A1 upon A2. Agreed? Now which area is more, which area is less? A1 is more, A2 is less. So which speed is more, which speed is less? V2 is more and V1 is less. હવે ઓલો સેન્ટેન્સ વાંચો, આ ફિગર જો. As clear as water. Is it it? Yes or no? Is it as clear as water? The sentence. The closeness indicates heat. When the lines are close to each other, it is more. When the lines are away from each other, they are less dense. It is less. Understood? Do you maths કેવી વસ્તુ સમજાવી દે? Do you agree with what I am saying? Right? So hopefully you all will remember that you have chosen maths. It means you are set for a very interesting ride where you can explain what's happening in nature around you. That is what maths helps you to do. આ equation વગર આ સમજાવવું હોય તો nearly impossible. Okay? That is everything now. I hope the second sentence is happy. So this also tells you, if you want to remember it, it is that where the area of cross section is more, fluid will flow slowly. Yes? No? Where the area of cross section becomes narrow, fluid will become fast. કેવું તમે કોઈ દિવસ જોયું કરીને? Do you realize that when you are having water flow in a pipe and you press your thumb and you close the pipe, have you noted that the more you close it, the faster the water comes out? Yes? No?
Yes.
નહીં? તેને દેખાય છે કે નથી દેખાતું આમાં? તો પછી ફિઝિક્સ ટેક્સ્ટમાં નથી. ફિઝિક્સ બહાર જોવાનું. હા, પણ ક્લાસમાં બારીની બહાર. Right? Everywhere else it is outside the textbook. Remember, you just have to train your eye and mind to notice the effects of what you are studying. Right? ખાલી બુકમાં જ બોક્સમાં બેસતો ને તો કોઈ દિવસ ફિઝિક્સમાં મજા નહીં આવડે. આ કંઈ આવડશે નહીં, મજા નહીં આવે, કંઈ નહીં. Right? I know some students always ask me, sir, ફિઝિક્સમાં તો આપણે કેટલા બધા assumption કરીએ, આમાં કંઈ સાચું જ નથી. સાચી વાત છે, તારે લેવાની જ જરૂર નથી. ફિઝિક્સ બે સબ્જેક્ટ ભણી લીધા હોત ને તો ચાલે. Because people don't realize that we are making only small assumptions. Right? Okay. So it doesn't mean everything is wrong. આપણે એમ કહીએ if you drop it from this height, it will fall. In how much time? If you want to find that, we can use equations of kinematics. આપણે એવા કેટલાય સમ કર્યા છે. I hope you remember. Okay? So we can predict the time. એમાં error આવે. Yes, I agree. There will be error because there is air resistance. But that error will definitely be small. 1 to 3% જેવી error આવે. Not a big deal. 100 માંથી 100 નહીં આવે, 97 આવશે તો ખુશ કે નહીં ખુશ? તો 3% error ચલાવો. Right? So we can do all of that which we have studied. Right? But just that you should be looking around your. બરોબર? બ્રેક મારો તો એવું ઇમેજિન થવું જોઈએ, ફ્રિક્શનલ ફોર્સ. Right? I can know that. Obviously the vehicle stops because of friction. Right? Okay. Open your textbook. We still have that part B of that question to be done. Am I right? I told you that we'll do it after equation of continuity. So now is the good time. I'm going to turn on the fans. I hope nobody minds it. It's terribly hot, isn't it? They are better. Will it feel hot? Okay. So that question, read it, part B. That's the description I want to put. I think there was something like a series with two parts. Am I right? What's the area? Yeah, connected. Like this, okay. And what's the bigger area? Diameter cube. So what's the bigger diameter? D1.
3 centimeters.
3 centimeters. Okay. What's the smaller diameter?
1 centimeter.
1 centimeter. Okay. Now what's the question? What is the question? If the smaller distance is
3 into 6 centimeters.
to 6 centimeters. 6 centimeters. All right. So let's say it comes till here.
Smaller.
I didn't hear that properly. I have to say. Yeah. So now this one is 6 centimeters. Then the question is, how much should this one? They will say derive the answer of it. You will realize that A1x1 is equal to A2x. Yes or no? Homework. આવું થોડો કરાવો એરિયા ફાઇન્ડ કરવાનો બરાબર ને Okay. Now Streamline Flow is done and question of continuity is done. It's time to take a Bernoulli's equation. We have time, hopefully we'll be able to finish it today. Bernoulli's equation. Bernoulli's theorem. The heart of this chapter. Okay. This is the point where you get most number of questions, right? But it's still quite easy. Do you know that there is a law of conservation of energy? Yes or no? Okay. So do you know that there is something called work energy theorem? Raise your hand if you know what it is. What is work energy theorem? The formula that is, okay, that's it. What is the work energy theorem? Okay, very good. Right. Put your hand down. First of all, I am making it abundantly clear that by tomorrow I want you to know this without fail. At any cost. ગમે ત્યાં ગયા હોય થઈ જવું જોઈએ કાલ સુધીમાં વર્ક એનર્જી થિયરમ must be clear to you. Got it? And now again I'm going to repeat this advice. Chapters 2 to 6 revise કરો નહીંતર તકલીફ પડી જશે હો ખરેખર. I don't want to see you all failing. Would you like to do that? Would you like to see yourself failing? The danger is real. તમને કહું તમને નહીં સમજ પડે. For example, this Bernoulli theorem is going to start with work energy theorem. પણ હવે work energy theorem ન આવડતું હોય તો પછી આપણો વારો ગોખવાનો જ આવે ને કે બીજું કંઈ થાય બીજું કંઈ તો શીખી જજો chapters 2 to 6. Alright, you have the notes, you have to read them. એક નહીં બે ત્રણ વાર વાંચો ન સમજાય તો મને પૂછો હું ક્યાં ના પાડું તમને બીજી વાર પૂછવાની પણ આવું નહીં થાય. I'm making it very clear. Yes, you. What's your name? Sorry? Divya. Okay, Divya, what is the work energy theorem? Very good, sit down. W total is equal to delta T. Clear? That is the work energy theorem. But do you remember that in chapter 6 when we used to do this one, when we used this, we were solving questions related to things like ball, block, solid only. This same equation takes a form. That form is called Bernoulli's theorem when you do it for fluid. Understood? This same equation takes a form that is called Bernoulli. એટલે કોઈ મને એમ પૂછે Bernoulli theorem શું છે? Work energy theorem. God. But yes, written in a different way. એટલે જોવાવાળાને ખબર ન પડે કે આ તો work energy theorem. But you will have to understand how we get it. Then you will agree with me. Right? So, let's begin. So for work energy theorem to be used properly and without a lot of complicated maths here, we are going to make a few assumptions. Number one, incompressible fluid will change. You already know that. We are going to use it. Right? Number two, steady flow. Steady flow means what? Streamline flow. Like I said, it is predictable, not random. Okay. Number 3 irrotational. What is meaning of irrotational? I'll explain that. Not at all difficult to understand. Let's say that there is some object, or let's say the pen. Suppose the pen moves like this without rotating. You see the difference? If you throw a pen, it will move and rotate. Yes or no? Yes. I'm actually having to explain this because we have skipped rotation. Neither the thumbnail method, right? So here the pen will move like this. Then that is not rotate. Correct? Agree with that? Yes. Okay. So how can such a thing be there in fluid? Let's say that there's a pipe. Okay, easy case. Don't draw this diagram. There's no need. If the fluid flows like this only, instead of going like this in a vortex, you understand the difference? The fluid particle arm thing is there. Then that is called which flow? Rotational. Isn't that? Go like this. The difference clear? Yes, no? Yes. Right? Rotating fluid. Generally what happens is when you try to make a fluid flow fast in a pipe, it will rotate. There will be rotational flow. Right? Okay, so obviously this is ideal. Incompressible fluid ideal. Steady flow also ideal. Irrotational flow ideal. Right? There is no doubt. Okay? So these are 3 assumptions that you should definitely remember. Nobody is going to ask you. तुमने खबर हो या यार तू derive करो. Okay? So keep these 3 in mind. Now, let's say that there is a pipe in which fluid is flowing. In a pipe, the fluid is flowing. And the pipe has different cross sections, or what I mean to say is, this area is A1, this area is larger, A2 for example. Okay? Clear? So here let's say the speed of fluid is V1, and over here the speed of fluid is V2. Not only that, these two are not at the same height. Not only that, these two are not at the same height. You can see this is lower, that's higher. So let's say that this is at a height h1. From where? From some ground reference. I hope you remember that when you want to talk about potential energy, there should be a reference. So gravitation का हमारा नीचे reference है, easy. यहाँ guys, equation does not change. Right? I'm taking it here so that this is at a height h1. Understood what is h1? And similarly over here, h2. Clear what is h1, h2, a1, a2, and v1, v2. Fine. Now I'm going to draw one more diagram. Can't get my two to this. The diagram becomes very untitled. You will not understand anything. Even I wouldn't get it what I'm drawing. Okay. So if you find that you can draw it in one diagram, I don't have a problem. But if you find that it's getting very clumsy, you draw 2, 3, as many as you. Okay. Again, like I have maintained it in past, I don't care what you write in your note. What I care for is what you can do in them, right? Or what you can tell me when I ask you a question. That's it. જરૂર પડે લખો જ નહીં, બુક જ ન લાવો તો નોટબુક ન લાવો ચાલો, કાંઈ જરૂર નથી નોટબુક લાવવાની, right? But if you are confident that you will be able to remember everything exactly as I tell you, right? And you never need to read it again, so no love. Okay. So here is the same diagram again. Okay, but you see the artist doesn't have that much scale, so please excuse the artist if the diagram looks different. Okay. Now, suppose here, because the speed is v1 in a time dt, in a time dt, the fluid will move from this part to this part, or this circle to this circle. That is, it will move a distance v1 dt. Is this clear? Okay, then displacement is equal to speed or velocity into time. But why am I writing d small? Define infinitesimal. So even this is going to be small. That's okay. Now just like that, here when this fluid moves here, this will have to move forward. So let's say it moves forward by how much distance? v2d. Yes or no? Did you understand v1 dt, v2 dt? If you understood both, raise your hand. आपको समझाएंगे वो जो ઊંઘતા હોય ને પછી એમને માથું ચોકર નાખ્યું એવું નથી ને. If you have questions, you can ask me. This is the right time to ask a question if you have not understood something. Please don't be scared. Yes. Louder? Not understood what? V1 dt or V2 dt? Both. Okay. What's your name? Smith. Smith. So Smith, do you remember that V is equal to what? V equal to V0 plus AT. Okay, not in that form. In form of time, dt and all that. Do you remember or recall any such equation? No. Do you recall the basic formula of velocity? What is the definition or what is the basic formula of velocity? Chapter 3. Yes. Not attended? Okay. Then let me tell you again. So it is going to be dx by dt. When dx is the small distance that it moves and dt is the small time in which it moves. Right? For differentiation of position with respect to time. Right? Okay. This one. So that's what we are doing. So small distance moved is how much? Dx equal to vdt. Clear or not clear? So vdt. So in time dt, fluid moves from cross section. Fluid moves from cross section E to Q and from R to S. Did you understand this sentence? Look here, read the sentence. Did you get it? Fluid moved from this cross section to this one, that is from here to here, and similarly from here to here. See, basically we are defining a system. Whenever you want to study something, what's happening, you have to define a system. So what was our system? Listen to this here. Let me use the blue pen for it, otherwise you will not understand. The system was all the fluid that was from P to R. So this, whatever fluid is in this blue boundary, that is our system. So we can say that what was here moved from P to Q. That's what we have written. Similarly, what was here at R moved from R to Q. So after the system, let's say this cluster is our system. So this is the right end of the system and this is the left end. So if this doesn't move from here to there, then we can say that the left end moved from E to Q. Similarly, right end moved from R to there. Absolutely clear. The only difference between this duster and the fluid is that these distances are not same. Duster ma same ho I hope you realize what I'm saying. જેટલું આ મૂવ થાય એટલું જ આ મૂવ થાય. Yes, no? Yes. Sure? એવું તો કોઈ દિવસ થતું નથી ને કે તમે અહીંથી અમદાવાદ પહોંચી જાઓ તમારા પગ હજી અહીંયા જ પડ્યો. That's what happens for solids when they don't rotate. Again, this is actually a property of not rotating. Rotate થાય તો એવું ન હોય. For example, if it rotates, this one is here. એમને એમ રહે ને આખું આમ ફરી જાય તો do you see this one moved but this one didn't. Okay, so get ready for rotational motion after this time. So that's our system, the blue one. So it moved from P to Q and R to S. But equation of continuity. Okay, so by equation of continuity, we should have A1 V1 dt equal to A2 V2 dt. Yes or no? Yes or no? Answer. A1 x1 is equal to A2x. Correct? Got it? Because these are equal, let's call this something. You know, it's easy to give it some name. Let's say capital B. I'm just writing a random letter. Someone say, look, don't write capital K and capital U. Capital K for kinetic energy, capital U for don't write P. P for pressure. Don't write F. F for don't write A. A for okay. So this is what we get. You can write anything actually. You can just say constant. Okay, volume remains constant because of that. So this is what we have. Keep this in mind. Now let's talk about change in gravitational potential energy. Let's talk about change in gravitational potential energy. Gravitational potential energy. Anyone remember that? U equal to mg. Very good. Okay, so we are going to do. But here we have a very nice trick. Listen to this carefully. At starting, when we started observing, the fluid was still here. That's our system. And till here. Again, that's our system. In this much time, do you realize that fluid moved this much higher? And similarly, it moved over here, right? Maybe higher or whatever, no problem. But do you also agree that in both the situations, initial and final, I think I'll draw that separately, otherwise you're going to have trouble. I remember that people had trouble last time. So this is the initial position of the fluid, of our system, yes or no? P to R. What's the final position of the system? Q to L. Okay, can you realize that the shaded part is common? Oh sorry, shaded part is not common, the remaining part is common, yes or no? Let me explain again. Look at this. અહીંયા સુધીનું આટલું common છે. Yes, આ બે લાઈનો છે. Because it was there in initial and it was there in final. Sure, you got it?
Yes.
This part has changed. This part has changed. But the one in the middle, that has not changed. There was fluid earlier and now also there is fluid. Initially and finally, in both the cases, there is fluid. And like I mentioned earlier, only the change in potential energy is important. So whatever is changing, that's what we will write. So delta U is equal. Initially, the fluid was in this part. You see that fluid was in this part, but it wasn't here. So do you agree that because we are only concerned about changes, આટલું તો ભૂલી જ જાઓ. આનું કંઈ જ કામ નથી. Why? It doesn't change. So how much here? How much is the potential energy of that? So final minus initial, final minus initial. So initial only this. Only this. Mass. Mass is like density into volume. Yes or no? Density, volume. Yes, no. A1 x1. And volume if this distance is x1 and this area is A1, how much is this volume? A1 x1. Yes or no? So A1 x1 rho density into 1 mass into g into height. How much is the height of this portion? How much is the height of that portion? h1. Clear or not clear? Who has understood that the potential energy of this part is this? Raise your hand if you have understood. Okay, there are still a few who have not got it. Let me explain again. The plan is as follows. mgh કરવાનો હોય ને mass કેવી મળશે? Density into volume of this part. Area A1, distance x1. So volume will be A1 x1. So here A1 x1. Okay, density into volume into g into h. But this volume A1 x1 can also be written as A1 into V1 dt because that distance x1 is ultimately V1 dt. That's what we have. Now similarly, finally, you don't have anything here, but you have something here. So we have any potential in your pattern. So what do you think we should write? What do you think we should write? Rho into A2 V2 dt G H. Okay, sorry, bad handed. A2 V2 dt and then GH2 and then there is a minus sign. Final minus. Again, we are only interested in change. કેમ ખાલી અટલાની પોટેન્શિયલ એની લખી સિમ્પલ ચેન્જ the common part is crossed out શું કામ લખવું જોઈએ કટ થઈ જ જવાનું હોય so I should be right got it because only the change is important so this is delta now just like this you have to tell me what is delta k on your own completely હું નહીં કરી દઉં ઉધીથી ફોર્મ્યુલા લખનાખી ફૂલ થઈ you tell me what should be right for delta k જેવું આમાં કર્યું change in potential, change in kinetic energy. Again, this part is common. What is the formula of kinetic energy? Half mv squared. Mama, half mv squared. Half mv squared. Do it. Come on. You have 2 minutes to give me the answer of delta k. Final minus initial. આ લખજો પછી પહેલા કીધું ઈ સોલ્વ કરો everyone try to get the answer that I'm asking you for anyone finished it delta k આટલી વારમાં તો આવી જાય છે just one line okay very good people yes you what's your name Ketu પહેલા તું આમ બેસતો હતો હું બેસતો હા તમે પ્લેસ ચેન્જ કરાવો એટલે નામ ભૂલાઈ યસ કેતુ વોટ ઇઝ યોર આન્સર half
Rho into
say it little bit louder than everyone here
half rho into A2 V2 dt square.
half rho into A2 V2 dt square square કોની ઉપર છે બધા ઉપર square
V ઉપર A2 V2
half rho A2 V2 square
A2 V2 square
A2 V2 square અને dt
dt
છે તો half rho A2 V2 square into dt minus half rho A1 V1
dt
તો square નો આવ્યું
square પછી
બોલ તો ખરો so you are saying V1 dt whole square
yes
do you get V1 dt whole square ખાલી V1 square આવે a cube આવે cube never mind get on well tried let me write it now let's see so I'm going to erase one of the diagrams here I don't want to write it in a very less amount of this calculus Arshal चुपट दे देते थे और Arshal फर्स्ट पेज पर नहीं देता Look this guy I'm joking sometimes I do joke right so delta k is equal to 1 by 2 final kinetic energy rho it is A2 V2 what is the mass yes or no yes A2 V2 square into dt sorry I forgot here clear or not clear minus half rho एक आवड़ी जाए तो बीजो आवड़ी जाओ got it final minus this you know what you can do you see this bracket appearing everywhere and it is equal to b yes or no so by the p login and after we'll do the next step clear what did I tell you for these things you can always write b okay we are going to cancel b in the next step goodbye yes what happened you don't like the fan is it